To correctly calculate the percentage fill of a cable tray containing a mixture of cables size 4/0 AWG and larger, and cables smaller than 4/0 AWG, it's important to address each group of cables separately before combining their contributions to the overall fill. Article 392.9 A3 of the National Electrical Code guides this process. Firstly, focus on the cables that are 4/0 AWG and larger. You must add up the diameters of all the cables that fall into this category. After summing up the diameters, multiply the result by a factor of 1.2. This multiplication converts the linear dimension, which is the sum of the diameters, into an equivalent area fill. This conversion is necessary because of how the larger cables are typically arranged in a single layer within the tray. Secondly, consider the cables smaller than 4/0 AWG. Here, instead of using the diameters, you'll be working with the cross-sectional areas. Add up the cross-sectional areas of all the cables in this smaller size group. This sum represents the total area occupied by the smaller cables within the tray. Now that you have calculated the area fill for both groups of cables, you need to combine these values to find the total area fill. This is done by adding the area fill calculated for the 4/0 AWG and larger cables to the area fill calculated for the cable smaller than 4/0 AWG. The result is the total area occupied by all cables in the tray. Finally, to determine the percentage fill, divide the total area fill which you just calculated by the maximum allowable fill area of the cable tray. The maximum allowable fill area is determined by the specific dimensions of the cable tray as specified by the manufacturer and in accordance with the National Electrical Code. For example, consider a 24-inch cable tray. This cable tray may have a maximum allowable fill area of 28 square inches. To find the percentage fill, you would divide the total area filled by 28 square inches. Then, multiply the result by 100% to express the fill as a percentage. The formula for the total area fill can be expressed as follows: total area fill equals 1.2 multiplied by the sum of diameters of cables 4/0 AWG and larger, plus the sum of cross-sectional areas of cables smaller than 4/0 AWG. And the formula for the percentage fill can be expressed as percentage fill equals total area fill divided by the maximum allowable fill area, multiplied by 100%. By following these steps, you ensure that the cable tray is not overloaded. Overloading a cable tray can lead to several problems, including insufficient space for heat dissipation, which can cause the cables to overheat and potentially fail. It can also restrict cable movement, making it difficult to add, remove, or rearrange cables within the tray, and it can violate the National Electrical Code regulations, leading to safety hazards and potential fines. The 1.2 multiplier for the larger cables accounts for the spacing between cables and the fact that they don't perfectly fill the space due to their round shape. This factor provides a more accurate representation of the area they occupy within the tray. When calculating the cross-sectional area of the smaller cables, be sure to use the correct values for each cable size and type. These values can be found in the cable manufacturer's specifications or in relevant tables in the National Electrical Code. Always refer to the latest edition of the National Electrical Code and local electrical codes for the most up-to-date requirements and regulations regarding cable tray installations. It's also crucial to consult with a qualified electrical engineer or inspector to ensure that your cable tray system meets all applicable standards and is installed safely and correctly. Proper sizing of cable trays is essential for maintaining the reliability and safety of electrical systems. By adhering to the guidelines outlined in Article 392.9 A3 and performing accurate calculations, you can ensure that your cable tray system is compliant, efficient, and safe. The calculation of cable tray fill involves understanding the specific requirements and applying the appropriate formulas for different cable sizes. To reiterate, the process involves several key steps. Firstly, calculating the area occupied by larger cables. Secondly, calculating the area occupied by smaller cables. Thirdly, combining these areas. And finally, determining the percentage fill relative to the tray's capacity. Let's break down each step in more detail, providing additional insights and considerations for accuracy and compliance. The first step in calculating cable tray fill is to determine the area occupied by cables that are 4/0 AWG and larger. This process involves summing the diameters of all such cables installed in the tray. The diameter of a cable refers to the measurement across the cable at its widest point, including insulation. These measurements are typically provided by the cable manufacturer in their product specifications. It is crucial to use the correct diameter for the specific type and size of cable being used, as variations in insulation thickness and cable construction can affect the overall diameter. Once you have gathered the diameters of all cables 4/0 AWG and larger, sum these values together. The result is the total linear measurement of the space occupied by these cables if they were laid side by side. However, cables in a tray do not perfectly fill the space due to their round shape and the air gaps between them. To account for this, the National Electrical Code requires multiplying the sum of the diameters by a factor of 1.2. This factor adjusts for the inefficiency of space utilization, providing a more accurate estimation of the area effectively occupied by these larger cables. The formula for the adjusted area fill of larger cables can be expressed as area large equals 1.2 multiplied by the sum of diameters of cables 4/0 AWG and larger. Next, you must calculate the area occupied by cables smaller than 4/0 AWG. Unlike the larger cables, where diameters are used and adjusted, the calculation for smaller cables involves directly summing their cross-sectional areas. The cross-sectional area of a cable refers to the area of the circular face exposed when the cable is cut perpendicularly to its length. This area is calculated using the formula for the area of a circle, which is pi multiplied by the radius squared, where the radius is half of the cable's diameter. Similar to obtaining the diameter, the cross-sectional area of each cable should be obtained from the manufacturer's specifications. These values are typically listed in square inches or square millimeters. Once you have gathered the cross-sectional areas of all cables smaller than 4/0 AWG, sum these values together. The result is the total area occupied by these smaller cables within the tray. Since these smaller cables can be stacked and arranged more densely, no adjustment factor is needed and the direct sum of the cross-sectional areas is used. The formula for the area fill of smaller cables can be expressed as area small equals the sum of cross-sectional areas of cables smaller than 4/0 AWG. Now that you have calculated the adjusted area occupied by larger cables and the area occupied by smaller cables, the next step is to combine these values to find the total area occupied by all cables in the tray. This is done by simply adding the area large and area small values together. The result is the total area effectively utilized by all cables within the tray, accounting for both the adjusted spacing of larger cables and the direct area of smaller cables. The formula for the total area fill can be expressed as total area fill equals area large plus area small, which expands to 1.2 multiplied by the sum of diameters of cables 4/0 AWG and larger, plus the sum of cross-sectional areas of cables smaller than 4/0 AWG. The final step in calculating cable tray fill is to determine the percentage fill relative to the tray's maximum allowable capacity. The maximum allowable fill area of a cable tray is determined by its dimensions and is specified by the manufacturer. This value represents the maximum area that can be occupied by cables without exceeding the tray's structural capacity or compromising heat dissipation and safety. To calculate the percentage fill, divide the total area fill by the maximum allowable fill area of the cable tray and then multiply by 100% to express the result as a percentage. The formula for the percentage fill can be expressed as percentage fill equals total area fill divided by the maximum allowable fill area multiplied by 100%. For example, if the total area fill is calculated to be 20 square inches and the cable tray has a maximum allowable fill area of 28 square inches, the percentage fill would be 20 divided by 28 multiplied by 100%, which equals approximately 71.43%. It's crucial to ensure that the calculated percentage fill does not exceed the limits specified by the National Electrical Code and the cable tray manufacturer. Exceeding these limits can lead to overheating, cable damage, and potential safety hazards. In addition to the calculations, several other factors should be considered when determining cable tray fill. Firstly, cable derriting, secondly, cable arrangement, and thirdly, future expansion. Cable derriting refers to the reduction in the allowable ampacity of a cable due to factors such as high ambient temperatures or the presence of multiple current-carrying conductors in close proximity. When cables are installed in a cable tray, especially in multiple layers, their ability to dissipate heat is reduced, which can lead to overheating and premature failure. To address this, the National Electrical Code requires derriting the ampacity of cables based on the number of current-carrying conductors in the tray and the ambient temperature. It is essential to consult the appropriate tables in the National Electrical Code to determine the correct derriting factors and ensure that the cables are adequately sized to carry the intended load even after derriting. The arrangement of cables within the tray can also affect its fill capacity and heat dissipation. Cables should be arranged in a neat and orderly manner to maximize airflow and prevent overcrowding. Larger cables should be placed at the bottom of the tray to provide a stable base, and smaller cables should be arranged in layers above them. Cables should also be spaced apart as much as possible to promote better heat dissipation. In some cases, cable ties or straps may be used to secure cables in place and prevent them from shifting or tangling. However, care should be taken not to over-tighten these ties, as this can damage the cables and restrict airflow. When designing a cable tray system, it is important to consider the possibility of future expansion. Electrical systems often need to be upgraded or modified to accommodate new equipment or increased loads. Therefore, it is wise to leave some extra space in the cable tray to allow for the addition of new cables in the future. A good rule of thumb is to design the system with a fill capacity of no more than 75% of the maximum allowable fill area. This provides a buffer for future expansion and ensures that the system will not become overloaded as new cables are added. In summary, calculating cable tray fill involves a series of steps that account for the size and arrangement of cables, as well as the tray's maximum capacity. By following these steps and considering factors such as cable derriting, arrangement, and future expansion, you can design a cable tray system that is safe, efficient, and compliant with the National Electrical Code.